Hello, Victor, and hello, everyone. Today, we will be hosting Victor, and as most of you probably already know, he is the author of a very powerful text formatting library named FMT. FMT is the underlying library that gave life to Stud Format, a library which was introduced to the C++ standard library with C++ 20 standards, and hopefully going to be the standard text formatting practice in modern C++. I want to specifically thank Victor for joining us today on behalf of the entire C++ Turkey community. So thank you, Victor, and welcome. So anyways, I'm going to leave the stage for Victor and let him explain a lot of very cool things about FMT and Stud format in much more detail.
Thanks, Sigit, for the introduction, and thanks for inviting me to give this talk. Let me start sharing. So the title of this talk is inspired by JavaScript, the good parts, but instead of focusing on good parts, which is obviously all of FMT, I'll focus on a few important and technically challenging ones and show how some of them are implemented and which C++ techniques I use. First, a few words about myself. So my name is Victor Zverovich. I work at Meta on the thread-RPC and Specialization framework. As you've already heard, I'm the primary author of the FMT library. We have lots of contributors right now, so shout out to everyone who helps in the development. You can go to the GitHub contributors page to see these folks. I'm also a self-proclaimed expert in -0, and you can find me on my favorite social network, GitHub, or on Twitter, where I post completely legit news about C++. So the first part of this talk will be dedicated to compile time. And it's not in the sense of how long compilation takes, but more about things that can be done at compile time for various reasons. And there will be three parts here. First, I'll talk about compile time checks, then format string compilation, and finally, compile time formatting. So let's start with the check. As it turned out, compile time checks exist in Printf today as a quality of implementation feature. So here, let me on my pointer. Bear with me. I'll connect my clicker. Oh, here we go. So here we can see a call to printf, where we're trying to format a string, but pass an incorrect format specifier. So we're trying to format it as a decimal number. And modern C++ compilers can diagnose it and give sometimes very nice warning, like this one, that format %d expects an argument of type int, but you passed a const star. So this happens if you compile with W format, so it's an opt-in usually. But otherwise, it's super nice. However, these checks are not perfect. Consider the following example of printing size t. So it's almost the same as before, but we're passing not a string, but a number of type size t. We try to format it as a decimal integer. And on some platform, you'll get a warning that you should you should pass actually LD. So it suggests this change here because it thinks that size t is unsigned long. So can you spot the problem in this slide? The problem is that if you compile on a different platform, say 32-bit platform, with the change previously proposed, changing to LD, you'll get the reverse warning, the opposite of what we had before. It says, oh, hold on, the size T now is just unsigned, so change it back to %D, which kind of doesn't make sense. So the Q part of QII, quality of implementation, is very low. Printf checks are lacking, but the idea is pretty solid. Fortunately, we can do better. FMT has compile time checks since version 5 introduced in 2018, so a long time ago. But previously, they were implemented using macros and Constexpr lambda trick. In version 8, released fairly recently, maybe a year ago or so, the checks are implemented using Constival and are enabled by default. Here's an example. It's pretty much the same example as we had with Printf. We're passing a string and try to format it as a decimal number. The diagnostic is not as beautiful, but it is enabled by default, which is an advantage. It gets the job done. It gives you enough information. So it says that the error happens in line 4, where we have our print statement, some context, and the actual error message is that it's an invalid type specifier. So D is invalid for the argument of string type. So yeah, hopefully in the future, we'll have mechanisms to good, also beautiful diagnostics and not just useful. And you can write your own function with compile time checks. It can be used in logging, compiler diagnostics, for example. Compiler diagnostics was the reason why I wrote FMT back in 2012 in the first place. I needed some nice API to report diagnostics in a parser I've been working on. So I decided to spend a couple of days on writing a formatting library. And 10 years later, here we are. So the way you write functions with compile time checks, so you just pass the format string as a special FMT format string type, which should depend on the formatting arguments T, and this will do all the magic for you. So it's pretty simple. So how does it work? It uses, it relies on 3 things, basically. C++20 Constival, which is essentially says that every call to the function must produce a compile time constant. So basically, it's a stronger version of Constexpr. The second thing it relies on is C++20 type identity, which suppresses template argument deduction. So this part is a bit subtle. I'll go over it later in more detail. And finally, we need converting constructors, which is C++98 feature, nothing cool. So here's a simplified version of the format string type, which only recognizes a single replacement field referring to an argument of type T. So instead of an argument pack as in real formatting function, we're just looking at one argument for simplicity sake, so that it all fits on one slide. Here we have a Constival constructor. This is an implicit constructor from a string. So S is a template, but basically it can be a char array. So if you pass something wrong, you'll get a compile error when you try to use it in the body of the function. But for simplicity, I didn't constrain this function any stronger. I just pass format string, the actual string literal as a template parameter. So in the body of this constructor, We do all the work as one usually does in C++. So we parse S and check if format specifiers are valid. So we go over every character. If it is a curly brace, then we check. So we only support the we check if it's an opening brace. Then if it's just a closing brace, we bail out, so it's okay. The default formatting is always valid, but if it's something more complicated, we construct the formatter and we invoke the parse function on this formatter. And parse function is Constexpr, so it's all checked at compile time. So this was like a generic format string version, which is parameterized on formatting arguments. And here we need to use the type identity thing that I mentioned previously. And the reason being is that we want to suppress type argument deduction. Otherwise, our implicit constructor won't be called here. So this is kind of a subtle and tricky bit. You can just take my word that this part is actually required. So this is mostly for the implicit constructor to kick in rather than template deduction rules to be used there. So we have our basic format string. We have our ls, which suppresses template argument deduction, and then we put everything together in a check function here, which takes a format string and formatting arguments, and we can check that it actually works. Our one slide implementation of compile time checks actually works. So if we pass a number, try to format it as a decimal, it works. If we try to format it as a string, it will give you a compile time error. Of course, it relies on the, if we go back, it relies a lot on the implementation of formatters. So some logic is hidden here, but otherwise, all the building blocks are there. Okay. So what do we do for user-defined types? So compile time checks also work there. For example, let's say we have a type called answer, which is a wrapper around integer, and we want to define a formatter for it, which supports a single format specifier x to format this integer as a hexadecimal. Otherwise, it will format as a decimal. So all we need to do to support compile time check is to make the parse function, which parses this format specifiers Constexpr. That's it. The implementation in this case is very simple because we don't support too many specifiers here. Again, because it's just an example slide code. So we go over the format string, which is stored in, accessed through the context. We check if the specifier is x, then we set hex Boolean variable, member variable to true. Otherwise, it's false by default. And then later, when we do formatting, we check this member variable and either format the value as hexadecimal or as decimal, which is the default. So as you can see, it's pretty easy to support compile time check for user-defined type, and it works. We can check it with FMT. So the first two lines here will compile fine because the default is okay. It will format as decimal. X we just implemented, it formats as hexadecimal. But if we pass an unsupported specifier such as D, it will give a compile time error. So this brings us to the second part of compile time trilogy, format string compilation. And a very limited form of format string compilation exists in Printf. For example, if we try to print a string with no replacement fields, a compiler may translate printf into putS, which is what we see here. So here we have printf, and with no formatting arguments, and the compiler magically replaces with a call to putS. It's pretty cool, I think. However, if we try to do anything even slightly more complex, such as formatting an integer, we get a call to printf with runtime parsing of format specs. So here, if you look at generated code, it is called regular as printf. No compiler magic. Again, we can do better than printf, and here is an example. So the CF user-defined literal here is defined in the FMT literals namespace, and it stands for compiled format. As the name suggests, it enables format string compilation. So instead of doing parsing of format string and specs at runtime, it generates an efficient code at compile time to format this. So in this particular case, the code doesn't have any calls or anything. What it does, it just stores a string for2 into buff, the output buffer. So it's like 4 instructions. And here are the building blocks for compilation, format string compilation. Obviously, we need Constexpr parse function in format specialization. We already saw them. The second is C++20 class types and non-type template parameters, which is quite a mouthful. It's shown as NTTP. Then we need C++17 feature Constexpr if. Strictly speaking, we don't need it. We could use template meta programming, but it's much nicer with Constexpr if. And finally, C++11 feature user-defined literal, but extended with C++20 class types in NTTP support. So this part is not exactly correct, not just NTTP, but class types in NTTP. So what are the non-type template parameters, or specifically, how can we pass classes there? C++20, let's say we want to pass a string as a template parameter. We can introduce a class template called fixed string here, and it has a constructor, Constexpr constructor, which takes an array of chars, where you can pass a string literal, and it stores it internally in the data member variable here. And the NTTP part is right here, where the fixed string template is passed as a template parameter. So we could do this in the format API, but it would result in quite awkward API where the format string would be passed as a template parameter, and arguments will be passed separately. It would interfere with argument indexing. So we don't do this in FMT. This is mostly for illustrating how we could use NTTP. The better approach, which is used by FMT, relies on user-defined literals and NTTP. So here, CF is a UDL, which returns compiled format parameterized on our format string, which we on fixed string that we introduced before. And if we look at the usage of this UDL, compiler simply transforms it into a call to operator CF parameterized on our string literal. And this string literal is converted into fixed string, and then the UDL itself returns the compiled format. So now we can use this compiled format in our formatting function here. This enables the API that we've seen previously. So format, where the format string is passed as a UDL. So all this magic applies. Actually, it's not too complicated. There are just some rules that we need to follow to make it work. But there are basically not too many parts involved. So once we have this, we can parse the format string using Constexpr if and turn into an efficient formatting code. In this basic example, we special case a single replacement field, translating it into a more efficient call to FMT toString as opposed to general purpose FMT format. Alternatively, we could use template metaprogramming instead of if Constexpr, but it would be much messier. So what we do here in format, we check if the format string is just curlies. If it is, then we know it's a default formatting. We extract the first argument here using a simple helper function defined at the beginning of the slide and pass it to string, so nothing fancy. And then when we actually use it here, it will be translated into a call to toString. So this is kind of a special case of format string compilation. And this is a pseudocode that illustrates how format string compilation works in general, as opposed to what we just saw, which was just one case. So given a format string, the compile function turns it into an object with a function called format, which does the actual work. Here we have a concatenation of a literal text. The answer is followed by a space with a field of type int and ID 0 and a code unit, or in other words, a character for a point, for a dot at the end of the sentence. So yeah. And this is a simplified representation of two compiled format types, text and field, from the previous pseudocode snippet. So text simply writes a string view to the output through the iterator, and field retrieves an argument given its ID and writes it. So ID is stored in here, the template parameter. So these objects of these types are generated by the compile function, and then at runtime, these format functions are called and do the actual work very efficiently. And this is kind of the general mechanism by which format string compilation works. If we go back to our original example, we can now guess that it's basically equivalent to a call to compile, which builds the compiled object, and the call to format on this object. So in the upper part of this slide here, we have this example from before. And the first stage is compilation. So internally, it calls this compile on the format string, turns it into this hierarchy of objects that know how to compile the, well, not hierarchy, list of objects that know how to format individual components. And then at runtime, the formatting is deformed on this using this object. And let's see how fast this actually is on the I2a benchmark by Miller. We compare format2 with compilation. FMT compile here, this is just a slightly more portable macro version of the CF UDL shown previously. Format2 with runtime format string processing here, which is the default, and we test printf, toChars, toString, and or strs to string, or str string, sorry. So sequential, so there are two benchmarks here, sequential and random. Sequential just means that the input is in the order of increasing digit count, which may be beneficial for branch prediction. As you can see, format string with compilation, where the FMT compile here is approximately as fast as toChars on sequential, slightly faster than toChars on random inputs. In principle, there is no reason for toChars and format with compilation to be different. It's just the choice of algorithms. Both are about 40 times faster than OSTR stream, which is quite impressive. Interestingly, runtime format string processing is not too bad, and comparable with the naive implementation of I2a, which is just a bunch of divisions in a loop. So this is a visualization of the previous benchmark for sequential. You can see how bad I streams are, and even as printf is surprisingly slow. So FMT with compilation and toChars have comparable perf, but toChars is slightly faster, well, in this implementation of the standard library, on smaller number of digits, while FMT is faster on more digits. One important advantage of FMT is that it can prelocate the buffer, which sometimes avoids copying. So the skeptical cat here has a question: why not make compilation the default if it gives such nice results? What is the catch? And the reason is that there is a trade-off between perf and binary code size. So formatting is rarely perf bottleneck, and when it is, you can easily opt into compiled format. The API is pretty much the same. All you need is put a UDL there. In cases like logging, which is often sampled, it doesn't make sense to generate a ton of bloat for code in many places that is rarely executed. So this brings us to the third part of compile section, which is compile time formatting. Yes, it's very self-descriptive. Here's a little example that shows how to convert an integer into a string at compile time. The only difference from the runtime format to invocation is that we wrap everything in Constexpr and carefully choose types that are Constexpr ready. So we use std array here instead of std string. I don't remember, maybe std string is actually Constexpr in 20, but this is more portable. So we create this array of fixed size. We call format to writing into this array here, and we need to do the compile time formatting. And what it compiles to is actually pretty cool. It just compiles to a static array of size 12, because that's what we chose with a string representation of 4-2. So 52 here is a ASCII character 4, and 50 is ASCII character 2. And then we have like 10 zeros. As you might expect, this works because we systematically Constexprified all the formatting code. Well, almost all. There are some restrictions with limitations with floating point at the moment. But there is one interesting caveat that I decided to mention. So this is static data in Constexpr functions. For example, in the format function, we use this count digits function that counts the number of decimal digits in the output for the given number. And there are some interesting optimizations. For example, the one by Kendall Willets, which uses a table, some lookup table. And what you would normally do is make it static. But unfortunately, if you try to add static here, natural thing to do, it will complain that table declared static in Constexpr function is not available yet, which is unfortunate. Or we can do non-static, and then it will generate you on a different compiler suboptimal code where the data is actually copied on stack or something. And the workaround for this is to define data outside of a function, let's say in some namespace scope or something like that. Yeah. So now let's go from compile time into something more dynamic. The next section is dedicated to Iterator. So FMT uses Iterator whenever there is a danger of excessive code load. And there are basically two areas where it can happen. There are three areas. There is also format string, but that's too minor to mention. So the first one is formatting arguments. So we have this nasty parameter pack of arguments. So if you're not careful, it can result in many instantiations of the format function. And secondly, we have an output iterator, which is also a template parameter. This is less of a concern, but because it's just for format 2, it's arguably less widely used format, but still. So FMT applies Iterator in both cases. But maybe code bloat doesn't exist and cannot harm me. Let's look at this trivial example with IO strings. How much code do you think it generates? And this is actually all the code that it generates, copied from, I think, Godbolt. There are hundreds of instructions, a bunch of function calls, and this is just for a trivial formatting operation. Very scary. And if we are not careful, it can be even worse with variety templates. If we naively implemented all the formatting logic in a variety function template, like format, it could result in an enormous code bloat. And this is actually what we see to some extent in folio format. Note that the string is particularly bad here. So here we have three different objects of three different types. Plus, we have three instantiations. And why is string the worst here? Because for string literal, you have an instantiation for every size, different instantiation for every distinct size. So to prevent this from happening, we use Iterator. The format function is forced in line. And all the work is delegated to vformat, which takes something called format args, which is a type array representation of arguments. And so, because we force inline format function goes away, and all these three things here are compiled into calls to vformat. The reason my clicker pointer is a bit slow. Sorry for that. So remember the iostream example from a few slides before? We generated hundreds of instructions. This is the equivalent with FMT, which is just a dozen of instructions and a single call to vformat, which I think is a nice improvement. Conceptually, it works as follows. An individual argument is represented as a variant of built-in types and a special handle for user-defined types. And a pack of argument is essentially a span of these variants. In practice, it's represented much more efficiently with discriminators of these variants stored separately and bit-packed. But this is kind of the main idea. So we have something called format args store, which has an array of these variants. Make format args just takes our actual arguments with non-type arrays and erases them and puts into the store. And finally, the store converts into this view, which is called format args. And the view is actually what we pass to vformat. So it's not that complicated, so it fits on a slide. It took a while to come up with this design that kind of, on one hand, is pretty efficient. On the other hand, doesn't cause code bloat. So skeptical cat here thinks that it looks familiar. And it does. It is actually very similar to printf, vprintf functions, which use var args. But the benefits of format args that FMT uses, that they are type safe, more efficient, and extensible. The efficiency comes from the fact that you can access every argument by its position, by its index in O of 1. With var args, you need to do the full scan or build the N array in advance, which is why positional arguments are much slower in printf. So this is one part. This was one part of type erasure. Another part is iterator type erasure in functions like format2. And for that, we use an internal concept of a buffer. And buffer is essentially three things: pointer, size, and capacity, which is just three simple member variables, and a virtual grow function, which can implement different strategies, how the buffer grows, how it flushes. And we have different implementations of this buffer. For example, Iterator buffer optimized for writing to a pointer, which is pretty common. You can have but maybe unsafe in some cases if used not carefully. You can locate a stack array and format to it. Be careful with writing past the end. But anyway, here we have iterator buffer specialized for the pointer, iterator buffer specialized for contiguous iterator, and iterator buffer for the common case of a non-contiguous iterator, which actually does buffering and then flushes into the underlying iterator, which is often way more efficient than writing one by one into the to the output iterator. And finally, we have something called counting buffer, which actually discards all its output. It is used in formatted size if you need to get the size of the output without writing anything. Okay. So bformat2 is essentially implemented like this. Kind of simplified implementation. So we take an output iterator, we construct a buffer from it, one of the buffer types that I just mentioned. We perform the formatting on this buffer. So bformat2, this version of bformat2 is actually type erased. It operates on the this type erased buffer. And then we get back the iterator and return it. And again, this version of bformat2 can be inlined, and so you don't have code bloat. Okay, so does it actually matter? As it turned out, it does. Otherwise, we wouldn't do this. In particular, here's an example where we achieved a 5x reduction in per call binary code size in the folio logging library by switching to this. And this was kind of just a small, just one part of the improvement. We actually achieved much better results in follow-up commits. And here's the final part of my presentation today about floating point formatting. So as you probably know, or if you worked with floating points, the formatting defaults are suboptimal, to put it mildly, in C and C++, so they lose precision. Here's a little example. If we try to write what is 0.1 plus 0.2, and separately what is 0.3, and then compare these things, you get completely nonsensical outputs, like 0 equals 0.3 equals 0.3 is false. Why it happens here? It happens because the default precision for cout and printf is 6, some magic number. So it actually hides, it loses information when you do the output. And this issue is not specific to C++, but some languages have better defaults. There is a site with this nice URL, 0.3004.com with some relevant information. So what are the desired properties of a floating point formatting algorithm? Obviously, we don't want information loss, what we saw in previous slide. We don't want that. Shortest output sounds nice, although not a deal breaker. We'll still discuss why it is important later. And correct rounding also sounds good, because correct is better than incorrect. So, and the last one is pretty much irrelevant with buffering. So it only matters if you write to a magnetic tape. So I'll refer to, oops, excuse me, I lost focus. So I'll refer to this set of properties, to the function with this set of properties as a unicorn. So these properties were written down by Still and White in the seminal paper in back in 70s, I think, but then it was republished in 90s. So first, no information loss. So kind of round trip guarantee. We want some hypothetical unicorn function here. So when you format with it a number and then parse it back, you want to get the same result, kind of round trip guarantee. We don't get it with Printf by default, which is unfortunate. And not just Printf, it actually many libraries and functions like this property, unless you explicitly specify big enough precision. Systed.io, C++ IOStream, toString, Python str format until version 3, many other examples of this lack of round trip. So how much digits we should print to get this to get round trip for IEEE 754? A double, we need 17 digits, which is a well-known fact from this paper. So the second property is shortest output. So we would prefer the number of digits in the output to be as small as possible. So because it's easy to satisfy the round trip property, but printing unnecessary so-called garbage digits. And here's an example. So if we call Printf and say 17 digits, you get round trip property, but the output is kind of rubbish because the string 0.1 is actually unambiguously represent the same number, and it is much more user-friendly. Okay, the third property is correct rounding. So usually it means round to nearest, ties to even, which is IEEE 754 default. Most implementations have this, but Microsoft, as usual, is buggy. Last time I checked was in 2015. I don't know if they fixed this issue. There were many posts about broken behavior in Microsoft runtime library. And the floating point formatting algorithms usually are Dragon themes. We'll look at what are the kind of state-of-the-art algorithms there. The Dragon comes not from the mythological dragon, but from the Dragon curve, which was the theme of the same Steele and White's paper I referenced earlier. So kind of state-of-the-art algorithms are DragonBox, developed very recently in Trendy by Junki, who kindly contributed the implementation also to FMT, where it is now the default. It's based on another awesome algorithm called Schubfach, developed recently. Really is pretty good as well, and recent. Then there is a family of algorithms called Grisu, and there are some very nicely optimized versions, which I use for fixed precision in FMT. Then there are original kind of general case Dragon family algorithms developed in 70s, 80s. And they are used as a fallback for exotic floating point formats in FMT because these nicer, faster ones are kind of special case for common IEEE formats. They are not. They may not work with weird floating points like double or even 128-bit. formats. So what does Printf actually use? So the full exponent range of the double can be pretty big. So in general, may require multiple precision arithmetic. It is not required in reality if you use one of those optimized algorithms, but glibc pulls in multi-precision library. I think it might use a variant of a Dragon algorithm. So if we look at the profile of Printf, or a Printf call with floating point, you'll see that it uses some point rate is really slow. Anyway, it uses npm, which is multi-precision library functions, multiplication, division with remainder, I guess, and something called hack digit. You know, something really curious is going on when you have a function called hack something. So what is the state of floating point in FMT? The default is shortest decimal representation with round trip guarantees and correct rounding. Our unicorn method, it has rich formatting, mini language, borrowed from Python. Supports iterators, size computation, buffer pre-allocation, has high performance. It is possible to completely avoid dynamic memory allocations for common floating point formats. Has locale control, with the default being locale independent. It's portable, requires only a subset of C++11, unlike, for example, 2chars, which requires C++17 and is not even available on most implementations of standard libraries. So here is a round trip example. We have the same number 1/3. We print it, we format it, get a string, read it back, we get the same number. Nice, easy. So this is the default, I should point out. Locale, so formatting is locale independent, as I mentioned, by default. If you want locale specific formatting, you have to pass the else specifier. For example, here, in some locale, it will replace decimal point with a decimal comma. And dynamic memory allocations can be completely avoided for common cases. And additionally, it's not necessary to specify the buffer size, which is different from 2chars. So we can get a single precise allocation and no extra copies. So you can't do it with 2chars. And finally, benchmark, little benchmark here from D2a Benchmark, again, based on Milo's nice collection of numeric benchmarks. So as you can see here, FMT is pretty much state-of-the-art, a little bit faster than Ryu, and we haven't even optimized the kind of integration between Dragonbox and kind of fancy precision with which adds formatting, which adds some overhead. So Dragonbox actually much faster than that. We just need to do some extra work to do integration a bit better. And here is the same data, but kind of graph over the number of digits in the output. So for so here you can see that FMT is faster on smaller number of digits in the output, and Ryu is slightly faster on larger number of digits, which is just how these algorithms work. Ryu is unusual in this sense. I think the desirable behavior is for shorter output to be faster, but it depends on your distribution of your data, I guess. If you only format random numbers, then Ryu might be better. So I lied to you, that was not the final thing. The final is a shout out to Hacking CPP for putting together awesome cheat sheets for FMT and other APIs. So this slide contains so much information in nice visualized form, and they have more. I highly recommend you checking out them. So this ends my talk, and I'm open for questions.
So thank you very much for this advanced talk on the very cool tricks you use to create FMT. I'm actually very impressed about the internals. I wasn't expecting this much of a complicated things going on in the background. So yeah, thank you for the question
sure.
part.
Hopefully,
yeah,
it was not too overwhelming. I know there are many details and many advanced features that's why I try to kind of extract the main piece and kind of present self-contained examples that you can go and try on Godbolt and implement yourself for mastering checks in a kind of few lines of code with this information.
Yeah. Yeah, thank you very much. I think it was very fun. The examples were they were very insightful, I think. I was also trying to replicate some stuff in the background while I was watching you, but yeah, I'll return back to this video after the stream. So yeah, we have a few questions from the audience. So Ozan asked, in which cases does it throw an exception, the format, I think?
Yeah, that's a good question. So in general, it throws an exception if there is an error during either parsing of format string or writing to the output. So writing is kind of unusual. You can get out of memory with some other error. So it most cases are kind of parsing, and with compile time checks, it actually eliminates all of that. So it eliminates the whole class of errors that would otherwise be reported as exceptions and makes them compile time errors.
Yeah, thank you very much. I think the second question is also kind of related with your answer. So ATTJ asked, is it possible to obtain a Constexpr string from a compile time formatted string? I know that it is not possible, but let's hear your answer.
Yeah, it depends what you mean by string. So if you mean string, then I don't think so. Maybe in 23, I don't remember what the status of string constexprification is. I remember that dynamic memory allocation, I think, is possible now. So it should be eventually possible. In my slides, I can actually bring up the slide. I showed how to do it for let me bring up the slide. Yeah, this one. So this is not exactly a string. You can wrap it in a string view, this array in a string view, and it's kind of like a compile time string in a sense, but it's not the string.
I see. Why? What's the reason that we cannot obtain Constexpr std strings?
So previously, the main problem, I think, was allocation, because in general it allocates. But now that I think dynamic memory allocation is available in Constexpr, I don't think there is like a fundamental difficulty. It's just maybe it's already possible. I just don't keep track of.
I think it is possible in C++20. I believe so.
Oh, interesting.
Right?
Maybe.
I don't know. I may be
wrong.
I thought
not, but
yeah. So thanks. It's not a question, but yeah, comment maybe I want to share. So Kyra says, you gotta love C++ templates. Anything is possible.
Especially code bloat.
Yeah. And Aaron said, great t-shirt, mate. So I think, I don't know if he's saying it to me or to, I don't know. So yeah, we have a good question here.
You have a Compiler Explorer t-shirt, right?
Yeah. I received it just today from Matt.
Nice.
Yeah. So Nejati asked, is there any accepted proposal for C++ 23?
I assume you're talking about formatting related, and yes, we have cool stuff coming. Well, it's still subject to final approval by the plenary in the committee, so it's long procedural work, but all the design and kind of wording is there and has been approved, so final stamp by the committee. We are awaiting that, but the features that might be likely coming to 23 are formatting ranges by Barry Rabzin. Great work. And secondly, std_print, which is integration of format with IO. So it will change how you write Hello World.
Yeah, finally. So thanks. I also have received some other questions, but they're not in the chat. I'll just read it verbally. So compared to FMT, what are some missing or different features in std format, and why were they not included in std format?
Yeah, good question. So with ranges, kind of, so ranges covers a big chunk of what was missing, but now I guess format string compilation is one big missing part. It's not also super important because performance of std format can be good enough for most cases. So it's not like critical, and we will probably add it in the future. Let me think what else is missing. Chrono is there, ranges are there, compile time checks are there as a defect report against 20, weirdly. Yeah, I guess not much, not that comes. There is some interesting IO functionality in FMT, which is sort of experimental. The API output file, which is a thread unsafe. So if you want to write very quickly from a single thread, this is super fast.
Yeah. Oh, thank you very much. We have another question from Nejati Argin. He's asking about std chrono formatting.
Oh, it's there in 20.
Yeah,
it's one of the main features. And kind of returning back to question about 23. So compile time checks, although they are not technically 23, they were adopted after 20. So in a timeline for 23, but they were applied as a defect report for 20. So it's sort of, I don't know how to characterize it. Is it 23? Is it 20? It was definitely after the 20 was released. And it was a big chunk of work.
Oh, thanks. Nejati Argin, who also has another comment. He says, I'm very happy to use and to teach std format. I think, yeah, I would agree on that.
Thank you. I'm glad that you are teaching that as opposed to like olden ways.
No, I completely appreciate it. A lot of people around us really appreciate this. So another one. what made you think that you need to build a library like this?
I was young and naive. I thought that it will take like a few days, and it will be easy, because the problem with the Printf I had, it was locale dependent, and iostreams also. iostreams had awkward API, so for compiler diagnostics, you want like an error message with some placeholders for arguments, which is basically Printf, but Printf is kind of problematic. It's unsafe and unextensible. So kind of these plus naive part.
Yeah, thanks. Nejati says, excellent library. Ahmed says, actually, we are using a lot a stud format library in our production project. Wow, that's impressive. And he also agrees that it's an excellent library. So let me continue with the questions that I had. So it says, we know that you have a very recently published proposal named toString or not toString. What kind of improvements should we expect in our code bases if it finally makes its way into the next C++ standard?
Yeah, there is a single improvement there, fixing floating points. So right now, toString with floating points is basically unusable unless you format things around one. One, because if you try to format a very small number, like 1 to the power of -7, it will give you 0. If you try to format a very large number, it will give you a ton of garbage digits. So that's my problem with it. And also it's localized. So I hope the committee will approve this. There are some potential concern about changing the behavior, but considering that it's only a floating point and the integer is unchanged, and it's kind of not super usable right now, maybe they will be okay with that.
Yeah, thank you very much. So another one, if you have time.
Sure.
Yeah, sure. So how would you compare boost format with stud format and FMT?
Yeah, boost is has very powerful mini language, and I think if I remember correctly, it's sort of compatible in a way with Printf through the grammar. So I think they extended it in a compatible way. But unfortunately, it's not super performant, and yeah, it's not very performant by design because they separated the kind of processing of the format string and building this kind of chromatic representation, capturing arguments at runtime. So it's kind of like compilation, but inefficient by design. So yeah, it was, I think, had the worst performance in benchmarks by far. But in terms of expressiveness, it's pretty powerful.
Yeah, thank you. So I think we have this last question. So it says, could you give me an example that you want to define as a feature for FMT, but the language doesn't support your way of doing it?
Oh, interesting. So one example was static Constexpr arrays, but I think they edited it. So judging from the warning, they edited it in 23 or something. Yeah, another thing, well, the extension mechanisms are a little bit hard. So this formatter specialization. So basically in C++, you have maybe 2 mechanisms for extension. You have ADL, argument dependent lookup, which is what iostreams uses, or you can do specializations, which is for what FMT uses, and none of them are good. So really, so specializations are okay, but they kind of verbose. So there are some proposals to add some better expansion mechanisms. the language.
Yeah, thank you. Do you have time for one more question?
Sure. Just tell me when we're ready to end, and I have all the time.
Yeah, we are bounded by your availability, so yeah. So one upwell says, not related to the format library directly, but what's your opinion on design by committee approach of C++? Do you think C++ lags behind for popular features like this because of that?
Yeah, I have mixed impression about design by committee. So there is definitely some negative aspect and slowness, slow bureaucratic process. But in my personal experience with stud format, it benefited greatly from the input from the committee. So for example, Iterator support came 100% from the committee. Before that, it was an awkward API that operated on buffers. So they said, no, this should be, Eric Nibler, I think, said that our way of doing it is iterators, and this was a design input, and which greatly improved the API. Another example was actually compile time check, I think, also was sort of mentioned. The idea how to implement compile time checks was somewhere coming from the committee, because they know all these weird ways of constival, implicit constructors. I think Richard Smith mentioned it in a kind of by the way matter once, and I kind of ignored it that time, but then it kind of came up much later and was implemented. But there are problems as well, and kind of it all depends, I guess, in many ways, whether the feature has a champion who is willing to spend a lot of time advocating, well, doing a lot of work and pushing it through the committee, surviving meetings. And so if there is no champion, then nothing will happen organically, naturally from the committee. And I think the lack of such champions is the reason why we have kind of gaps in some parts. The work is not, so people are doing it on their time mostly. Some companies sponsored this work, but or at least are okay people spending some of their time on this. But otherwise, many just do it as a hobby and not paid.
Yeah. So thank you very much. Speaking of the committee, so do we have Unicode support in stud format?
To some extent. So most of the formatting is encoding agnostic, but we managed to sneak in, but don't tell the committee, but we managed to sneak in some Unicode support so that if you have UTF-8 encoding, which is like the case for most sensible people projects right now, it will just work. And it will do it not in an old horrible way by querying the locale, but determine it statically from the kind of what is the static literal encoding. So it's very UTF-8 friendly, and in print it will be even better. Well, in print it's more visible because it crosses the process boundary. So with formatting, it's just operating. You give it something, and it just concatenates things and like adds spaces. There isn't much encoding there, although you still need to interpret the string and in some way. But with print, it's more tricky. So we spend most of the review, this 3 years or something, in the Unicode study group arguing about like absolutely every aspect of it to make it work reasonably well.
Yeah, thank you very much. So we have another question. Before that, one up well. Thanks for championing this such a great feature.
I had great support, so I must thank Howard Kinant in the first place, who encouraged me to write. Who was the first committee member I contacted, and he was very supportive, and the other committee members were super supportive.
Yeah. So let's move on to the question. Osan says, which STL implementation do you find most comparable to FMT library?
If you mean that format, we don't have implementations. Then we don't have many of them yet. So the most complete, I guess, is an MSVC. Then there is one in libc++, which progresses very well. It's less complete than Microsoft's one, but in some ways it's a bit better.
Thanks. So we have another question from Kyra. He says, the answer to most of the studs feature question is, if something you like is not in the standard, it's probably you're not there to implement it. So I think this is not a question, but yeah, comment.
More of a comment than a question.
Yeah. Ahmed says Clang has implemented it in the last version, 14.
Yeah.
Oh, it's good news.
It's not 100% complete, but they made a very good progress, so you can use it now. There are some limitations with the load and chrono.
Yeah. So I think we have run out of questions. We don't have anything inside. Yeah. So thank you very much again for teaching us all these very interesting things, very useful information. We hope to see you again in such a, maybe in real life, we host you in Istanbul.
Thank you very much. Yeah, thanks for inviting me and hosting this wonderful session.
So yeah, should we end the stream? Yeah, okay. Goodbye.
Bye, everyone.